to be honest, I'm really excited to be here to share with you the details of this project that we've been working on for quite some time now. And there are many things to talk about, but I guess it would be a successful outcome if, so by the end of this talk, you'll kind of get the feeling of what you can do with this project that we've announced this morning, understand the core concepts of the SDK, have a kind of intuition about how it is implemented on top of Flink, and get an idea of how to get started. So let's start with, what is it all about, this thing that we've announced this morning? So that's essentially a new SDK for building distributed and stateful applications. And this SDK, it's supposed to help tackling those common challenges that you would face when building stateful applications. Now, by now it's quite understood, and there are quite a lot of good practices how to deal with stateless applications. Essentially, you have this n copies of your stateless instances just running around, and you have a load balancer in front of them, and you just have to select let's say the least loaded or the most healthy instance and route the request there, no problem. But when you start talking about, when you start editing state into the mix, stuff gets much more complex. So one thing that you have to start thinking about is how do you partition your, essentially your compute and your state? How do you, how do you scale? And when you figure out the partitioning, then you have to start thinking about, okay, where is the actual physical instance that handles the data of user X? Where is it? What's its host name? What port do I have to connect? When you get that figured out, then you have to start thinking about how do I communicate with it actually? What is the semantics that I require for the communication? Is it exactly once, at least once? What happens if I send an increment request? Would that be incremented twice in the face of a failure? Those are things that you get into quite fast when you're building stateful applications. Just to mention a few of those. Now, when thinking about it, that's really the bread and butter of a stream processor, and specifically something sophisticated, a sophisticated stream processor as Flink. Those stuff are already present there, those building blocks of how do you partition your computation and state across many nodes. How do you route messages? How do you perform a shuffle, essentially? And many more. And this is what we set up to do, actually. We set up to see what kind of building blocks we can take from this modern, sophisticated stream processor and bring it to the application development space. So that was our goal, and so to summarize, so it's an SDK for building distributed stateful applications. The core concept is this addressable virtual functions that encapsulate local state. Those functions can send messages to each other. Sorry, those functions, they can message each other within arbitrary communication patterns. It's not restricted to a direct acyclic graph, as you probably used to do while writing Flink programs. And this framework plus the implementation, they support exactly once state and message and consistent snapshotting. So I hope that gives you a little bit of an understanding and motivation. What are we actually set up to do here? And at this point, I'd like to go over the SDK overview. Let's just go through it. So this is sort of a bird's eye view of a logical stateful application. So you'll have functions that are communicating with each other. There's event ingresses that ingest data into the system, and there are optionally event egresses that might communicate the data out to an external system. So let's start with the functions themselves. So basically, applications are collections of those stateful functions that are bundled together. So each function, it can react to an incoming event. It can perform some local computation, can adjust its state, a local state, and send messages to any other arbitrary function, and possibly also emit messages to an external system, say a Kafka topic or something like that. They are addressable. So let's talk about this concept of an address. So each function is associated with a function type and an ID. So you can think about a function type like roughly like as a class in an object-oriented kind of world, and an ID as something that uniquely identifies that instance. So if you combine those two, you get an address. And addresses here are logical, are not physical. Like there is no, they don't contain host and port, right? They contain some user-defined something with a business value information inside of that address. So. And this is essentially the partitioning by an address. So this is how the runtime would essentially parallel those stateful functions by this address. So you can see here for an example, we have like an email sender function that receives the, let's say, brown messages are directed to the stateful function instance with buzz at bar. And the blue ones are for food at bar. Let's actually see code here. So we have a stateful function that essentially greets, computes some personalized greeting. So the first thing that you would see that we have here this invoke method. Now, this invoke method would be called by the runtime when the message is received to that stateful function. And we know that we only expect messages of type greet request. So we cast that generic input, and we compute something local, like compute some personalized greeting for that specific user. And at that time, we decide to send this recommendation, the personalized greeting to some email function. You can assume that this email function is, I don't know, perform some batching or something like that, or some rate control, so we will not flood and spam the user every time they come into the system. So all we have to do to send a message to that instance of a stateful function is basically to compose this address where we specify what is the function type and what is the ID part of it, the key, and we just say to the stateful function framework, send this message to that address, and that's it. So let's spend one moment to talk about what is the actual execution model here. So when I was mentioning that there is a single instance of a stateful function per an address, we are really talking about a logical instance. We're not talking about a physical, like a Java object that's being allocated for each address. And what really happens behind the scenes is that the runtime would swap in the correct state just before the invoke method would be called on your stateful function type. And from the user perspective, it would feel like you have a single instance. But what we will be doing is basically multiplexing state for each incoming message. So you can think about it as a, let's say, as a process function. You don't have a new Java instance for every incoming process function message, right? You kind of expect the state would be managed by the runtime. So this is exactly what happens here. And you can look here at the bottom. Here's an illustration. So conceptually, the logical view of things is you have your two instances. Function type would be fn, and there's this key user1 and fn and user2, and they both have their state. It's independent. But in reality, the physical view, you would see that those messages are they're interleaved, and there is a single instance of this function type, and the state is being multiplexed by the runtime. Another important aspect to mention is that the instances are created on demand. Like, you don't manage the lifecycle of it, you don't have to think about it. They are being created by the system when the first message arrives. And they are already ready to process those messages, and that's pretty convenient also from the sender perspective, where I don't have to care about is this instance is currently alive or not, like the shard that is dealing with my user, do I have to think about it? So we know that the instance would be transparently created for us by the runtime. And another thing to mention is that since we have a single instance that serves a single address, logical instance, of course, messages that are sent to a single address are processed sequentially by effectively a single thread. So this might sound familiar if you're familiar with the actor model, for example. And another important property is that if you send messages from function A to function B, you can assume that they would arrive in a FIFO order. And this is very important if you're writing protocols or you're basically implementing a state machine. You don't have to deal with out-of-orderness inside of your protocol, which can get really, really tricky quite fast. So we keep saying that's a stateful thing, but let's actually talk about state. So the way to define state is inside of your stateful function, you basically you can define a persisted value field, and you can use that field as if it was a normal field inside of your methods, inside of the stateful functions. So you can dereference it, change it, and do whatever you want with it. And the system would transparently make sure to for fault tolerance, essentially to ensure fault tolerance in that case. So since those kind of applications, we kind of assume that they would be long-lived, long-running, you may want to think about how to evolve them. And to have those applications evolvable, you must use a type for your state that supports evolution, schema evolution. Now, what we support out of the box would be protocol buffer, and that's what we recommend as well. And so it's built inside of the SDK and the runtime. And I think most of the examples that you would find on the repo would actually be using protocol buffers. And of course, you can use JSON as well and Avro, but this would require more careful consideration. So to get started fast, you can also start with non-evaluable types, but it's the practicality is not very useful for production. Okay, so let's talk about ingresses and egresses. So basically, you need a thing that starts. So ingress is basically the thing that pushes data into your stateful functions application and starts the initial computation. So a message from the ingress would find its way to an instance of stateful function. We'll talk in a second about how it's actually finding its way, but it would be essentially the first event that triggers the computation, and then the messages can start messaging each other, percolate until, I don't know, they can decide to emit a message downstream to an ingress, for example. And what we currently support out of the box is Kafka for an ingress and an egress. So that would be a part of the SDK. But of course, you can use essentially any Flink source or sink as an ingress or an egress as well. So yeah, so let's talk about how an event, like the initial event, actually finds its way from an ingress to the first stateful function. So there is a concept of routing, and basically, a router would actually determine which function to invoke at the beginning, and so the way it works is routers are attached to an ingress, and you can attach multiple routers to an ingress, and each router would be invoked on every incoming message from the ingress. And basically what you have to do is you have to supply an address for that incoming message. So I have here a GREET request. I know that it should go to a GREET stateful function, and that is keyed with that user ID, and then just will be forwarding it. And you can decide by inspecting this message that you will be dropping it on the floor, for example, because it's not applicable, or you can actually create a fan out. Like you can send a single message to invoke multiple functions, creating like sort of a pub sub kind of thing. And this is only required for moving the data from the ingress to the stateful functions, and then they can already start communicating by addressing each other directly without any routing. So I think, okay. Yeah, so at this point, I'm gonna talk to you about I'm going to show you some code. I think Stefan already showed in the keynote the end result and talked about the ride-sharing app that we've built to demonstrate those capabilities of stateful functions. So what do we have here? So my goal for this demo is to give you like an insight of how you can structure stateful applications, how you can use the fact that you can have a stateful function essentially per entity, and show you some code as well. So this example basically has drivers and a passenger that are communicating with this stateful function application through the ingresses and egresses. Now, drivers, they constantly communicate their current location, and passenger basically request a ride. They say, I'm at point A, I want to go to point B. So now the next thing that I want to mention is that, so we implemented that with those 4 stateful functions that are essentially state machines, and they are communicating with each other. So the driver and the passenger, they represent like an actual physical driver and an actual physical passenger. So you have a logical instance for each physical driver. So you'll have it here. And the same for a passenger. So let's briefly just go over like one flow of a driver sending its location update. So when a driver sends a location update, there would be a web app here or something like that that would push an event into Kafka. This is my driver ID, that's my location. This event would be consumed, would be routed to the relevant driver stateful function. Now, this driver stateful function, it knows its current address and it knows the updated address. So if it's a different one, it can choose to update the Geo index by sending it a message. You know what? I'm driver 7, and I'm also free to take rides, and I'm going to join that cell, and or it also can say, I want to leave cell number 15. You can think of Geo cells like Geo hashing. And so let me show you how does it look like at code. So I cannot go over every detail here, but I try to show at least 2 functions here. And yeah, so let's start actually with the Geo cell. So the Geo cell is a stateful function. So much like the fact that we have a stateful function for each driver, you can think of this Geo cell that there is a Geo cell instance exists for each Geo hash Geo cell. And drivers send messages to it, and they say, I want to join or leave that Geo cell. So the thing that you would have to do here so the first thing you would know who called you. Like the context provides a caller, so you'd know the address of your caller. So that is useful because if you want to reply to your caller. And what you'll have to do is essentially pattern match here as what kind of message is it? So is it a driver that's requesting to join cell, leave cell, or is it a ride function that asks to get a free driver that belongs to that Geo cell? So let's assume that's a driver that wants to join a Geo cell. So the thing that we are doing here, we were basically asking, we are dereferencing our state and adding that driver to the current list of drivers that we know and set the state back. And that's all what this function does. I'm going to skip the get driver, but you can imagine like it would essentially fetch the state and find a driver that is eligible to take the ride. So we can, this would be pretty common, like people would be doing that all over, this kind of pattern matching. So there is a slightly more sophisticated way to do it, but that's, so it's like a utility class that you can extend from instead of implementing the stateful function directly, which basically you have the, so you can just declare ahead of time what kind of messages are you expecting, maybe also supply some predicates like about the content of the message, and then attach a function, a piece of behavior of what to do when this message is invoked. And so looking at the function driver, now this piece of behavior deals with a pickup request that comes from a ride. So the driver can first check if it's taken or not, and if it's taken or not, and if it's if it's basically taken, that it can reply directly to the ride and say, sorry, I cannot pick up this passenger. Otherwise, the driver would remember the ride ID, and then has a bunch of logic that relates to actually picking up the ride. So first it would notify the Gale cells, so it would send a message to the Gale cell here that says I'm leaving that current Gale cell. And then it can also say to the ride, I'm joining this ride. That's my ID, and I'm here. In addition, it also has to notify the physical driver somehow. So the way to do it is with this ingress. So basically, you use the same mechanism. So context.send, you specify the egress, and this is a message, an outbound driver message. It's a protobuf message. So I apologize for the verbosity, but this message would end up into the whatever egress we've defined, and that would, in that case, in that example, that would be a Kafka topic that would be consumed by the physical driver. So the physical drivers are free of any state coordination or something like that. It all happens in the stateful function, in the stateful functions application, but they just get command and they can send like status updates, and that's it. And this is how we think it should be. Like the edges should be fast, efficient, but stateless. And the kind of the core coordination and the core the state machine of the business logic should be stateful and should have very strong guarantees as well. So I'm going to skip the visualization. I hope you've seen it this morning. Let's actually have a peek under the hood and try to understand how it maps to a Flink job. So this is a logical logical stateful function application where you have ingresses, routers, and functions. And so you can see there are some routers attached to an ingress and some functions. So what actually happens here, so this slide is slightly involved, but bear with me. So that's the actual job graph and the layers and the operators that you would find. And it's not super complicated. There are not many other operator types or so. There's like 1, 2, 3, 4 layers, and this whole thing is implemented there. So it's so as you can probably guess, ingresses would be mapped to a source functions and changed to a flat map that would multiplex the different routers that are registered in the system. So once the message leaves the flat map operator, the source plus the flat map operator, it's already packaged in an envelope. So the user payload and the address, everything will be serialized there and will be set on this envelope. And then we would key by which partition by the destination address. So messages that are directed to a specific stateful function instance would land to a specific function operator instance. Now, the next layer is the function operator. So this is the operator that essentially invokes those stateful functions when messages arrive. Now, each operator knows all the function types that are defined in the application, and given the type of the incoming message, it would select what to invoke. The next thing is the next thing is that we have to solve is how do we essentially communicate sideways, because this function might send a message to that function, but it's not very straightforward to do. And the way we are doing this with these iterations, with feedback implemented, and the way it works is there is another key by here and another set of operators that are basically collocated with the actual operators. And this key by, so if this one wants to send a message here, it would first have to forward to this feedback operator, which magically would be collocated with the same instance inside of the same JVM. And we can use a side channel to basically reapply this, reintroduce this message into the main processing loop. And this entire thing is the messages that are flying here on the wire, they are all checkpointed and as part of the normal checkpoints. Of course, there are also the sinks that corresponds to the egresses. I did not add a line here because it would be too many lines, but you can assume that from the function operator, you might get here as well a communication channel. So let's look at the function operator itself. Okay, let's actually go over the flow. How does it look like? So there are incoming events. There are different types of payloads. And after a key by of the target address, so the first thing this operator would do, it would actually figure out what's the target function, what function should I invoke for that. Then it would load that function. So this is if it's not already loaded, it would create a new instance of it. Then it would set up the environment that is relevant, scoped for that specific message. So it set up the key, the Flink key, and everything that we need to essentially prepare to invoke that function, including class loading and so forth. The next thing would be we'd actually call the invoke method of that function. So we'd unwrap the user payload, deserialize everything, and just send it, call this scoped function. This function, while processing, can update its state and decide to send messages downstream to either sideways or to a sink, to other functions. So this is the thing to note here, that when I mentioned that this is a logical instances, that really is the case. There is a single, essentially a singleton. There is a single Java instance for every function type. But that just creates the illusion that you have many, many different instances by swapping in and out the state. So let's quickly talk about how do you actually deploy this thing. So I'll run through it, but essentially there is another SDK concept that I haven't mentioned yet. There's this stateful function module, which is basically the entry point. So application is actually a collection of those kind of modules that are bundled together and submitted. So you can have many different modules like that coexist, maybe even created by different teams. And the configure method is where you can actually bind everything. You can bind your functions, like function factories and ingresses and routers and so forth. And what would happen is the system, the runtime, would discover all of those stateful function modules and basically will wire up the entire application and translate all of those stateful functions concepts to a Flink job. And so how do you deploy that? So there are at least two ways. One is in the Dockerized environment, where this project also comes with a Docker image, a stateful function Docker image that already includes Flink in there and is configured. And basically what you have to do with this Dockerized environment, you add your module under module, so you can have full bar bus, doesn't matter, and attach your jars there, copy your jars there, and once you build it, you can start it once as a master and many times as a worker. And those would actually form a Flink cluster behind the scenes. So from the user perspective, you start with the stateful function base image, you add your jars, add modules, and launch it. There's another way of launching it. If you have a Flink deployment at the moment, so you basically create a Uber jar, a fat jar, and you add that dependency there, and you're good to go. You can submit it with the command line, with the Flink CLI tool. So how do we get started, actually? So we made the, so there's a website, statefun.io. You can visit there, read all about it, and follow the docs. The repository is opened, and you can visit it. It's our Verica GitHub repo. And you can ask questions, maybe in Stack Overflow, use the statefun keyword so we can find it and we can respond there as well. Yeah, I think leave some time for questions at this point. If anyone.
Hi, thanks for the great talk. I have a question about this state machines. You mentioned a few times that it's under the hood, there's a state machine. And is there any overview of what my state machine is? Because I'm most probably defining a business process here, a distributed, scalable, stateful business process for this ride-sharing application. And do I have a global overview of what's going on and what's the business process?
Right.
Or are they really separated from each other? So yeah, so that's my question.
Right. It was state mission, you said? Or
yeah. State machine. Yeah. So
okay. Okay. So right. So yeah, there are many layers here, but let's really from the operational perspective, every state function type declares a metric, so you can know how many messages came in and out. So they, in the operational perspective, you can see that. Now, one huge advantage of implementing this thing about Flink from the business the business perspective that you were mentioning is that you can actually have a consistent global snapshot in point in time of your entire application, all the stateful functions, all the instances there. You can just basically take a snapshot, and you can analyze it with the tools, other tools that Flink offers. So you have a running thing in production that serves some sort of traffic, let's say, but then you can have periodically copies to be analyzed by, let's say, a business analyst, data scientist, so forth. So that's a very powerful feature, I think. Does this answer your question?
Yes, thanks.
Cool.
I'd like to ask, is it possible to integrate the stateful functions inside another job with a streaming application, or do they need to be in a standalone job and communicate over the network or something like that?
Yeah, that's a great question. We want to make a better story of how to embed stateful functions into existing Flink pipelines as well. I think, so technically it is possible. I have to think about the details later, I guess. We can chat later if you want, but I think it's possible.
Hello? Yeah, so this is regarding the, here.
Oh, sorry.
This is regarding the feedback loop. So how does it impact window boundaries? Because there is a potential of, infinite loop.
Right.
So how do you tackle that technically?
Right. So currently, the type of processing time semantics that is supported at the moment is processing time, right? So so you mentioned windowing, right? Right. So an out-of-the-box stateful function application currently doesn't have the concept of windowing, but this would also something that we might introduce.
Okay.
Yeah, if I understood your question correctly.
I think from your answer, looks like it's on the roadmap, not yet implemented, something like
so
that.
So windowing, like as a windowing state or something like that, possibly. But like besides windowing, this whole thing is checkpointed consistently. Like the loop itself is also fault tolerant, with the same mechanism that you would expect in other Flink applications as well. Do you want to? Yeah, Stefan is here, so he can maybe comment more. This is like a different perspective.
So maybe if I understand the question correctly, what do you do if you have if you have functions that are sending messages and it stays in the feedback loop forever, right? So this is a bit of a broken case, right? I mean, imagine you have something like, I don't know, imagine you have a service, you call it, and it basically infinitely starts ping-ponging with another service, right? This is kind of the same situation. If you actually have a function that keeps sending messages, the message comes back, it keeps sending it out, and it kind of never drops it at any time, right? Then you've pretty much built a program that's just like ping-ponging requests and never leaves it. I think what would currently happen is, yes, these would go around, and they would probably eventually take up the processing capacity and kind of start back-pressuring messages from the outside world. So it's a very, very fair point. Like having a bit of observability and traceability into these scenarios is definitely like this is I think what Igal mentioned earlier. We're looking a lot into like how to add metrics to exactly discover these cases, but I think it's the same as in many other. In many other setups, you can build something that just doesn't make sense, right? You can always build something that doesn't make sense, and then this thing is not going to save you from that.
My question is about the state performance. It felt like from the diagram that we're loading the state in each message. I was wondering, did you experiment with large states, and how is that loading and updating performance going on?
Right. So when we say we swap in state, we actually mean that we set up the key context behind the scenes. So if you will request state, then so it's basically as a normal Flink application that uses, let's say, a process function that is applied by different keys. So it has the same underlying implementation, more or less.
But isn't Flink more? Flink operators are more physical. Like they don't really. You don't really change the context constantly.
You change the state, right? You change the key. You get you get a message, a record for key A, then key B, key C, but you still have a single instance of your flat map, right? So the state backend abstraction, that's what it does, and we use the same mechanism.
All right.
Hi. Is it possible to update the stateful function in runtime?
Right. So that's a very good question. So would you actually like to do something like that?
Because I thought a serverless, like a function always you want to deploy a single function in some point of time and update it.
So So at runtime. So right. The thing is that you can do it. Not out of the box. Conceptually, we can implement something like that, but we decided actually to stick with this concept of immutable deployments, where you should know what is running at a given time, and you don't swap in and out functions. But we 100% convinced that we will just stick with the immutable deployment. Maybe that would be a good idea also to implement something like that. It's actually one of the reasons why we open source that in now and not like in 2 years, where we have like a complete story and so that's exactly the kind of feedback that we are looking for example.
Thank you.
Yeah.
Hi. Stefan mentioned during the keynote that you were possibly able to replace the Kafka queue with a HTTP server or something like that. Mm-hmm. Are you doing any work on the queryable states? So you can set up like subscribe to state keys or some subscription states and stuff for on the input and egress functions as well.
So queryable state. So okay. So the way to the recommended way to communicate with the stateful function world is by sending messages to the function and getting a message back. So that would be the way to go. Having queryable state is I'm not so sure what is the state there at this point, but we can think of. And maybe have a better story there.
Yeah, no, I mean like the Amazon API gateway that calls the Lambda, that you're able to get a response to the same server that made the call.
Right. So in our initial iterations of this, we actually had something like that, but we decided not to include it in this release, but. So the problem with HTTP or RPC in RPC, essentially, what you're describing is that what do you do with fault tolerance? Essentially that's the big question there, and you need to come up with a story that makes sense for the community.
It's okay.
But you can totally use let's say an HTTP ingress, but you in the case that if the stateful application job fails, for example, and then you have to deal with that, like you have to deal with the dangling request or something like that.
I wanted to ask, for the implementation, this is totally built on top of Flink. So you were able to build all of these using your API, or you had to change something in the runtime?
So very minor stuff, like exposing stuff, was needed. It already existed there and used internally by different components. But that's almost completely user code, basically. Like in the lower levels of the user code, like in the abstract stream operator level, but yeah. Okay.
So basically, the feedback loop is implemented with side inputs, side outputs?
No. It's implemented with assigning a collocation constraint on 2 different operator types, making sure that they're keyed in the same way. And then there's also the fault-tolerant aspect of it that uses something else. We can chat about it later if you want, but it's totally, it's like a totally an indication of how powerful Flink is. Like you can actually build stuff like that on top of it.
So only another thing. So I suppose that if you get an infinite loop, basically you break fault tolerance, right? Because you get a checkpoint only when you get to sinks.
I'm sorry?
If you get an infinite loop, you break the fault tolerance thing because you get a checkpoint only when you get to egress, right? If you reach a sink, you can get a snapshot.
No, not necessarily. Okay. Not necessarily. But we can talk about it offline.
Thank you. Thank you.
All right, one more question, and then I think others are having lunch already. So one question.
Is that feedback operator available as a separate library?
No, it's there. It's available as a separate Java package, if that helps.
That helps.
Yeah.
Enjoy the break.